space of A as well. Okay? And so, again, A was my favorite matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I want to describe what's called the row space of A. It says the row space of A, by definition, is the span of the rows of A. And again, there's all this vocabulary. By the way, a week from today, I'll be giving you your vocabulary bonus quiz, custom made for you to help you learn vocab. I'll explain more about that maybe a little later. But what does span mean? Do you guys know what the span is? That's why we need a vocab quiz. It's the set of all linear combinations of the rows of A. It's the set of all linear combinations of the rows of A. So there's another vocab word. This is why it's just a foreign language right now. You ever had a math class where you've had so few numbers and so much vocabulary? What are linear combinations? Can you tell me what those are?
Isn't that where, like, if you have three vectors,
Mm-hmm.
you can add two vectors to get three vectors?
You can either add them. That's one thing you're allowed to do. There's one other thing you're allowed to do to be a linear combination. Well, subtract is adding the opposite. So yes, I agree. You can subtract.
Multiply by scalar.
You can multiply by, so again, addition and scalar multiplication. Those are the two things we're allowed to do. So can we do that with the rows of A? Well, sure, watch. You could do this. When I say the row space of A, one way to say it is, it's the set of things that look like this. Take the row 1, 2, 3, right? Multiply it by any constant that you want. I'll call that C1. Add it to some other constant, C2, times the row 4, 5, 6, right? And add that to some other constant times the vector 7, 8, 9. Okay? So if you can imagine what that set looks like, then you understand what the row space is. Okay? So what I'd like you to do is come up with a vector that is in the row space and come up with a vector that is not in the row space, if you can do that. Okay? And I'll pause while you guys come up with examples. It's a race. Whichever group comes up with the one that is and one isn't is the winner. Go. Another one that's in. So Tyler says 12, 15, 18 is in the row space because you could make C1, C2, and C3 equal to 1, right? And that would give you 12, 15, 18. Okay? How about this one, guys? Just 5, 7, 9. Is that in the row space? Yes, but do you see what I'm doing?
C1 is 1, C2 is 1, C3 is 0.
Yeah, so these are kind of easy examples. You can let the constants be anything you want, and you'll get something in the row space. Here's a question. Is every possible vector with 3 numbers in it in the row space or not? I don't know. Give me a vector. We'll decide if it's in the row space.
20, 11, 3.
Did you just kind of make up some numbers?
Yeah.
What do you guys think? Is it in the row space? That's the question, right? How would I decide? Well, what I really have to do is say I'm setting this equal to that, right? And trying to find C1, C2, and C3 such that I have linear combinations that give me the pink vector, right? Now I want to point out that this is equivalent to doing the following. Imagine I wrote the pink vector like this, right? If I wrote it this way, then I could write these vectors 1, 2, 3, 4, 5, 6, 7, 8, 9, also as column vectors, right? And I'm throwing a C1 here, plus a C2 there, plus a C3 there, and I'm basically solving a system of equations. How do you do this?
So you're allowed to turn it to, I like looking at it as a column.
I like looking at it this way too. I didn't because we're talking about the row space. But I'm going to now so that we can actually you guys know how to solve this system, right? Sure. That's why I pulled MATLAB out while you guys were busy working. And I already typed in this matrix A, although that's not quite the right matrix, right? I want A transpose. Do you remember how to get that in MATLAB? Yeah, you do the apostrophe. A apostrophe. There, that's the matrix we're talking about, right? And let me do this. Let me say that B is going to be the matrix. Okay, so you guys have 20. Oh, wait, I need a matrix notation. 20 semicolon 11 semicolon 13, right? This is what, that's what Anthony picked?
It was 3, not 13.
Oh, was it? Oh, you're right. It was 3. Because look what I did.
That makes sense.
It does, doesn't it?
Because now that I kind of read about this to do some of the homework,
Yeah.
you can do the row echelon form one way, this is the other way they say,
Yeah.
and this way is what's easier. And that makes sense why now.
Good. I'm hoping that you guys come to class and learn some things, so that's good. So let me do this. Let me put together a matrix. Matrix M, I will call the matrix that I get by augmenting A prime and B together. So M is this matrix, right? And now, what do I have to do? I have to reduce row echelon form that matrix M, and this should tell me whether or not it's in the span. Did that tell me somehow? Well, remember what you have to do is you have to rewrite what those equations say. And you all start at the bottom. So what does the last equation say?
0 equals 1.
0x plus 0y plus, or 0c1 plus 0c2 plus, yeah, equals 1. So this thing, we notice, has no solution. So what did we just prove? We proved that not everything is in the row space of A. There are, a lot of things are, but some things aren't. Are you with me? That's okay? Not everything in R3 is in the row space of A. Yeah?
I was just going to ask if you could explain what the difference between doing it this way or having the vector testing, like past the equal sign, on the bottom and then leaving it in the row form.
Yeah. So it turns out not much. There isn't much difference. And I kind of feel like I need to explain a little more before I can get to the answer to that question. Because all of a sudden I started working with A transpose, right? Okay? And there are some theorems in this section that kind of explain it. Okay? But let's hold off on that. Come back to it. If I haven't answered it by the end of class, I'm not doing my job, okay? Let me know. But let's do this. I'm trying to describe what the row space looks like. Oh, is the row space a subspace of R3? So that's the next claim. Row space of A is a subspace of R, I'm going to say N. For us, right, this is 3 by 3. Remember, we always like to do M by N. So the claim is that the row space will be a subspace of Rn. If I want to prove that, I guess I need to know what it means to be a subspace, right? Do you remember what you need to show that something is a subspace?
It has to contain a 0.
Okay. So the first thing is it true that the 0 vector is in the row space of A? Well, I guess in our example, what would the 0 vector look like? It would look like this, yeah? Is that in the row space?
Yeah.
Yes, because you just let C1 equals 0, C2 equals 0, and C3 equals 0, and then you get. Yeah, so that works. And what's the other parts that we need? Is it true that row space of A is closed under what? Addition and scalar multiplication, because, how do we know? Well, there's a word I use that kind of implies already it's going to be closed under addition and scalar multiplication. Because how's the row space even defined? It's defined as a span. And what is a span? It's what you get by doing addition and scalar multiplication, right? Because it was defined as the span of the rows of A. So I would say we have just proved, because we got addition, scalar multiplication, and the 0 vector, we just proved that row space of A is a subspace. So you've learned that null space is a subspace of Rn, and you've learned that row space of A is going to be a subspace of Rn. Now, if it's a subspace, then the next thing we ought to be able to do is find a basis for the row space of A. That's what we want to do. This is what we reviewed today. We want to find a set of vectors that will span the null space and be linearly independent. Okay? So how do you do it? Well, this is where I'm going to use a cool fact from the reading. Cool fact, sometimes called a theorem. So it is true that doing row operations to a matrix does not change the row space. That's very useful. So I want to use that fact. Okay? I guess what I just learned is that the row space of my favorite matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, will be equal to, move that so you can see a little better, the row space of let me do this, guys. Let me go to MATLAB, and let me just throw my favorite matrix back up there. Okay? Oh, or I could do this. I could say matrix N is my favorite matrix, and I'll put some zeros next to it. The book doesn't do this, but I think when you're first learning, it's kind of instructive to do this. Why am I doing this? What does it look like I'm about to do? Find the what? The null space, right? And you're right, if I did reduce row echelon form of n, basically this would be telling me the null space, right? But it would also, right, if I did reduce row echelon form of A, wouldn't I get the same thing basically? I'd get this, right? And so what I'm saying is this cool fact tells me something. It tells me that the row space of 1, 2, 3, 4, 5, 6, 7, 8, 9 is exactly the same as the row space of 1, 0, negative 1, 0, 1, 1, 0, 0, 0. These row spaces are the same. And that's interesting. Because if these are the same, one way to describe the row space I did up here. But another way to describe the row space would be like this. It's the set of vectors C1 times 1, 0, negative 1 plus C2 times 0, 1, 1. That's it.
So the C1 times the matrix of the first row plus C2 times the second row is the answer of the row space of your matrix. So if you were asked to find the row space of your favorite matrix, would you put the C1 or would you put something like the 12, 15, 18?
I mean, you're asking a good question. Did I ever ask you guys to find the row space? I said, let's describe it, right? And I did say, let's find what? A basis for the row space. A basis. The reason you have to do that is, you guys, how many vectors are in the row space? Well, the answer is infinitely many. There's all these different linear combinations of the rows. But what I'm saying is, you can find a basis. Again, what are the requirements for being a basis? There are two. We need, so again, maybe I'll throw it here. A basis B would be such that we need the span of B to be the row space of A, and we also need B to be, B must be linearly what? Independent. So, I guess what I would say is, you can see that if you take these three rows, well, by definition, the span of those rows is the row space. By this cool fact, you could just use these two rows. Is that true? I should check that. What were some of the ones that we said were in the row space? You guys used, oh yeah, 12, 15, 18. Can I get 12, 15, 18 from these? I guess I could check, right? So if I go to MATLAB and I say V1 is the vector 1, 0, -1, and I'll put an apostrophe so that it goes on its side, even though it's a row. And if I say V2 is equal to 0, 1, 1, and put that on its side, right? Now I have the two vectors that I'm saying gives us the same row space, right? So now I can try and get some of these vectors that you came up with, right? So I could say S1 for solution number 1 is, I remember we went with 12, 15, 18. And so now I can make up a matrix M1, which is V1, V2, S1. Right? And I'm going to ask, does this have any solutions? Let's find out. No. Because the bottom one says 0 equals 1. Which says we did something wrong, guys. So glad I'm recording that. So that's the error, is that there's a 2. So let's fix that. It's not 1, 0, -1, and 0, 1, 1. It's 1, 0, -1, and 0, 1, 2. Okay. So let me go back and try it again. V2, the last element is supposed to be a 2. 0, 1, 2. Yeah. So now again, I want M1 to be this matrix where there's a 0, 1, 2 for the second vector. And now I want to reduce row echelon form M1. That's better. Okay. So what did we learn from this? We learned that C1 has to be 12 and C2 has to be 15. Actually, I should have been able to do that by hand, right? Because if you make C1 equal to 12, that'll make the first number equal to 12. And if you make C2 equal to 15, that'll make the second number equal to 15, right? And does it work to get 18? Well, yeah, because what's 2 times 15? 30 minus 12 gives me 18. You see that? So you can get any of these elements this way. Oh, but like you still can't get the 2011 3. Remember you guys did this one? Trying to get 2011 3? That's still not going to work. You'll still get no solution. Okay? So, again, because of this cool fact, this guy's span is the same as this guy's span. So that's nice. But the other thing we need is we need B, the basis, to be linearly independent. These 3 rows, are these linearly independent or linearly dependent? The 3 rows in my favorite matrix. They're linearly dependent. Because, again, we showed that. If you take my favorite matrix and throw some zeros after it, right? And if you reduce row echelon form that, you get infinitely many solutions. But what about these two vectors? Well, these are linearly independent. Because if you set this equal to 0, the only way to get these to equal 0 is to make C1 equal to 0 and C2 equal to 0. You guys with me? Okay. So, let's answer the question. Can we find a basis for the row space of A? What's the answer? I guess it would be 1, 0, negative 1, and what? 0, 1, 2. That's right. That's one possible answer. Is that the only answer? No, not really. You actually just need two vectors from the row space that are linearly independent. So that's the other cool fact, is that I guess what really matters is what's called the dimension. So again, let me go back to what this section is all about. I think it's time now. Again, most important section in the entire book, section 3.5, is entitled Subspace. I think we know what that is based on what we just did. Basis. Do you remember what the other two words are?
Dimension and rank.
Dimension, which I want to explain again now, and rank, which we really haven't talked about much yet. Although we did like in chapter 2 a little bit. So I'll come back to rank in a second. Here's my question, guys. What is the dimension of the row space of A? 2. Because a basis has to have two vectors. Dimension 2. And I want to come back to talking about rank. Do you remember what we said was the rank of a matrix when we first talked about it?
It was a number of non-zero rows.
It's the number of non-zero rows if you do what? If you reduce it. Like, what is the rank of my matrix A? It's 2. It's not 3. Because what you do is you reduce it, the bottom row becomes all zeros. The rank is 2. And notice that's the same as the dimension of the row space. So here's another way to define rank. The rank of the matrix is the dimension of its row space. Okay. So let's talk about rank for just a second. The rank of a matrix is equal to the dimension of its row space. Now here's the big theorem. The reason I say it's a big theorem is because it actually has a title. The rank theorem. Here it is. Suppose A is an M by N matrix. Then the following is true. The rank of A plus what is called the nullity of A has to equal N. Now again, maybe just to to rephrase this, the rank of A, remember, is the dimension of the row space of A. The nullity is also a dimension. It's the dimension of the null space of A. And it turns out that has to equal n. Always. This is called the rank theorem. And in our example, n was equal to what? 3. Yeah, we had a 3 by 3 matrix, right? And in our example, the dimension of the row space was what? 2. And in our example, is that true that the nullity was 1? Yeah. What was the one vector that we used as a basis for the null space?
0.
No.
Was
0 vector can't be a basis. The 0 vector is always in the null space. Let me go back to it, because we did this last time. There it is. Remember we said all the vectors look like this? So what vector do you use for the basis? I don't know. Either this one or that one. Basically, the only one you can't use is the 0 vector, right? But the point is you need a single vector. So what is the dimension of the null space of A? It is 1. The dimension of the null space of A is 1. Okay? All right. 10:50 I think is a great time to stop. Give you guys a 10-minute break. So maybe the first one to go over, since you didn't have the answer in the back, is number 10 from the homework. Some of you guys got it, some of you guys didn't. It says, suppose S consists of all points in R2 that are on the union of the x-axis or the y-axis or both. S is the union of the two axes. Is S a subspace of R2, Y, or Y not? So let me draw the world of R2. This is something that you guys are pretty familiar with, right? Here's R2. Well, actually, that's interesting. I said this is R2, but didn't I just kind of draw S? Right? I mean, R2 is a plane, right? But S is all the points in R2 that are either on this axis or that axis, right? So here's S, right? And so the question is this a subspace? Is S a subspace of R2? What do you guys think?
No.
You say no? How come, Tyler?
It's not closed under addition.
No. Not closed under addition. How come?
Because the set contains both the x and the y, the combination of an x and a y
Mm-hmm.
point would equal something that's not in the set.
Right. So for example, if I took this point here, which is maybe 2, 0, and if I add it to 0, 2, when I add those, what do I get? I get 2, 2, right? And so 2, 2 is, right? 0, 2 plus 2, 0 equals 2, 2, but the problem is that this is not in S, right? Does that make sense? So there's an example of something that, a set that is not a subspace. That's right. But interesting, number 9, you were actually asked to prove that if you have a line through the origin, it is a subspace, right? Because it'll contain the 0 vector, it'll be closed under addition and scalar multiplication. It's just that this is not. Okay? That was one thing people asked about. And then when we got like to 17 and on, some people had trouble with that because I I hadn't gone over like all the directions yet, right? So it says, like for number 17 or 18 or 19, give, that's the plural of basis, right? So find a basis for the row space of A, for the, what's this?
Column space.
The column space of A and the null space of A, okay? So I've done null space and I've done row space, but I haven't done column space yet. I should probably do that, right? Let's do that now. Let's talk about how you find a basis for the column space of A. Well, maybe we should do the example we've been doing, my favorite matrix. I always do that, okay? So let's find a basis for the column space, again, of 1, 2, 3, 4, 5, 6, 7, 8, 9. That's what we want to do. Now, what is the column space? Again, this set is the span of the columns of A, right? So it would be the set of things that look like this. C1 147 plus C2 258 plus C3 369. Okay? So it's funny because it's very similar to the row space, right? It's just using different vectors. You're using the columns this time. All right. So did you guys read any nice facts about the column space when you were doing your reading? Because there are some nice facts here. Well, it's interesting. If you think about it, isn't it true? Here's a fact. The column space of A has to be equal to the row space of what? A transpose. That's right. I mean, that makes sense, right, guys? That's by definition. So one way to do this problem would be this. Here. I want to find the column space of A. There's A. So what I can do is I can reduce row echelon form not A, but what? A transpose. Right? What do I get? I get this. Hey, does that look familiar to you? That's the same thing I got when I did this. Dun, dun, dun. Coincidence? Not a coincidence. Okay? But it is interesting. It is interesting. So, one way to do this problem, you say, what's a basis for the column space of A? Well, I guess what I could do is I could find a basis for the row space of AT, and so I could use 1, 0, negative 1 and 0, 1, 2. One, 0, negative 1 and 0, 1, 2. So that's interesting. But I guess here's where you don't have the whole story yet. And you almost don't get the whole story until after we cover 3.6. And maybe I should share a little of that with you now. Let's do that. So 3.6, this is introduction to what are called linear transformations. So linear transformations, I'm going to let you do the reading for Thursday and understand what they are. But I'm just going to tell you that basically linear transformations are maps from one space to another. And here's kind of the idea. We can think of an M by N matrix as a map from Rn to Rm. And I think the best way to understand this is actually to give you an example. And so I'm going to take problem 17 from last night's homework. Okay? This is section 3.5, number 17. You had this problem. It said A is equal to, and they gave me this matrix, 1, 0, negative 1, and 1, 1, 1. Okay? By the way, what size matrix is this? 2 by 3. And so according to what I just said, it is a map from where to where? Well, it's interesting because it's M by N. Right, it goes from the world of R3 to the world of R2. So let's draw a picture of it. In R3, we have, it kind of looks like this, right? X, Y, and Z. But R2 doesn't look like that. R2 looks like this. Maybe I'll just call this Y1 and Y2. Actually, I don't know if I want to call them Y's or not. Oh, that's all right. So, I don't like Y's. Let me call it, how about I call it U and V? No, I don't like that either. How about I call it M1 and M2? These are the axes, but it's the normal graphing world that you're used to. And then this is more like the Calc 3 world. Okay? So the next thing I want to do, guys, is I want to graph on here, I want to draw a picture in green of the row space of A. So give me some vectors that are in the row space of A. Well, that's easy. One of them is 1, 0, negative 1, right? So where would that be? Well, that would be 1 in the x direction, 0 in the y direction, and I would have to go down 1 in the z direction, right? So down to here. And so the row space of A would include this vector, right? That's 1, 0, negative 1. And the other vector that it would include that I could draw would be 1, 1, 1. And so I'd have to draw a cube, right? And I would have to kind of draw an arrow from 0, 0 to there, 1, 1, 1. Okay, see that? And if you were to graph the whole subspace of this matrix A, all the linear combinations of those two green vectors, what shape would it be? Well, you would need a sum, so you'd have to add these two vectors. Do you believe me when I say what you would get is kind of a plane coming, you know, it has to contain those two, right? But there would be a plane right through those vectors that's kind of like that. Does that make sense to you guys? You couldn't leave that plane by taking linear combinations. Are you with me? So that's the row space. Oh, but anyways, what happens is, if I pick some generic vector, so let me pick a generic vector. Let me come out here. So what point is that? Looks to me like that's 1, 2, maybe 3, 3, and maybe it's down 1. So maybe this is the point 3, 3, negative 1. And the reason that this matrix is a map from R3 to R2 is you can take an XYZ, put it in here, and so what you get is you have the map AX equals, I'll call it B. I should have called these B1 and B2. B, if you think about it, look, I have a 2 by 3 matrix, and I'm going to multiply by a point. That's 3 by 1. I'm going to get a 2 by 1. That's right. So this is going to be a 2 by 1. It's going to be some point in R2. So I asked you guys, where does 3, 3, negative 1 go? Well, I guess I could work it out, right? It gets sent to 3 of the first vector plus 3 of the second vector plus 1 of the third vector. No, negative 1 of the third vector. So let me work out what that is. 3 plus 0 plus 1. It gets sent to 4, comma, 3 plus 3 is 6, minus 1 is 5. 4 comma 5. So it gets sent here. 4, 5. So somehow this point gets mapped there. Are you with me? Okay. Now, by the way, you could do this. We can go back to one of our questions we were asking earlier. What is the null space of A? Now you can think of it as the set of vectors that get mapped to 0. Right? Where? When I say 0, I really mean what? The 0 vector. That one. Guys with me? So the null space, here, let's see if we can say, what's the null space of this matrix? Well, how do you compute it? You're going to go null space of if you want a basis for the null space, what do? You're going to do reduced row echelon form of 1, 0, -1. We're trying to make that equal to 0, and we're trying to make this equal to 0. Yeah? Here I go. Reduced row echelon form of the matrix. It would be 1, 0, -1, 0, and then 1, 1, 1, 0. And when we reduce row echelon form, I get this. Boy, that keeps coming up. 1, 0, -1, and 0, 1, 2, 0. So we get, well, okay, the first row stayed the same. 1, 0, -1, 0. And this one became 0, 1, 2, 0. And so, what does the null space look like? Well, I guess the bottom equation says y plus 2z is equal to 0. And what's the top equation say?
X minus z equals 0.
X minus z equals 0. So you might remember how we deal with this. We say z is equal to t. And once I do that, I know that x has to equal t. Right? And then I guess y has to equal -2t. Right? Oh, so once again, what's the null space of this matrix? What would be a basis for it? So I could say, as a basis, so if I want a basis for the null space of A, how many vectors do I need for a basis for the null space? 2? 1?
2,
Well, let's see.
the row echelon form of A, rank
So the rank is 2, right? What's the rank theorem say?
it's rank plus null
Equals
equals
n. And n is what in our example again? 3.
There's only going to be 1.
There's only going to be 1. And it would be, for example, you could put t equal to 1 and use 1, -2, +1. So let me graph that. 1, and I want to graph it in pink. Come out 1, -2 in the y direction to be this way, -2 in the y direction, and up 1. So somehow this vector going to 1, -2, 1, that one right there, anything along this line, that's all right, any multiple of that vector gets mapped to this single point. Isn't that weird? All this gets mapped to there. Because it also, anything in the null space has to get mapped to 0. So yeah, I mean, one of the points of section 6 is that we can think of matrices as being maps from one space to another. And all these things we studied, these subspaces show up. Okay? Now, related to what Tyler asked me about, A transpose. Okay? What does that look like in this picture? Let's see. A transpose would look like this. It would be 1, 1, 0, 1, negative 1, 1, right? What's its dimension? 3 by 2. Therefore, it is a map from where to where?
R2 to R3.
R2 to R3. And it turns out, right, A transpose maps things back. So A maps things there, A transpose maps things back. So when I say that the row space of A is the same as the column space of A transpose, yeah, you're kind of just switching them. And so I guess what we learn from this kind of idea, okay? So let me go through kind of some basic facts to sum up. Okay? And maybe this kind of puts it all together. Suppose A is an M by N matrix. Then row space of A is a subspace of Rn. Okay? Null space of A is a subspace of Rn. And of course, these two are related, right? So the dimensions of these subspaces will add up to n. That's the rank theorem. Now we have another space, like I said, called the column space of A, right? But that's the span of the columns. Where does the column space live? Well, look, the columns of A, they're all elements of which space? R2. See that? 1, 1, 0, 1, and negative 1, 1. Those all live over here. So I guess what we say is the column space of A is a subspace of Rm. The column space of A is a subspace of Rm. So there's a reason that I feel like if you want to understand this stuff, a square matrix is okay, but it's better to use something like we just did, 2 rows and 3 columns, so you can see the 2 different spaces. That's kind of interesting. If you talk about the rows, you're talking about like one space, which was the pre-image of the map. And then you're talking about the image of the map when you're talking about the other space. By the way, what would be the column space of A? Sure, it's the row space of A transpose. So in our example, did we compute that? let's see. No, I guess we didn't. But here, oh, you could. Here's A transpose, right? So if you wanted a basis for the row space of A transpose, look what you do. You could add the first row to the second row and make that a 0. And then you could add negative these to make that a 0. So you could make that bottom row both zeros, right? And you'd be left with this as in row echelon form. So basically, the first two rows could give you the column space. And so if you used 1, 1, and 0, 1, how much of R2 would you get? Here, let me do that in green. Suppose I use 1, 1, that's that vector, and 0, 1, that vector. Isn't it true you could get anything in R2 by adding those two vectors and doing scalar multiple? Yeah, that was that example we had the very first class. Remember we had the funny graph paper? But isn't it true you could kind of get anything from this? You could. So it'll span all of R2. So there were three things you had to do. First thing it said is find a basis for the row space of A. Right? How do you do that? Well, again, if A is 1, 0, negative 1, 1, 1, 1, the big thing to do, right, is do row operations. You don't have to do reduce row echelon form, but you need to at least get it into row echelon form, right? Why did I have to do that? Because I have to be careful. I have to be careful that I don't have the things linearly dependent, right? Actually, I guess for this example, I knew right away we were okay. I knew that we were not linearly dependent because when you take these two rows, right, 1, 0, negative 1, and 1, 1, 1, I know they're not scalar multiples of each other. If you only have two, that's easy to see. So the row space, again, is this plane that goes through 1, 1, 1, and, right? So let me give you two possible answers. Find a basis for the row space. One answer would be 1, 0, negative 1, and 1, 1, 1. Or another answer would be 1, 0, negative 1, and what was the other thing we got when we did MATLAB? 0, 1, 2. Because remember, doing the row operations won't change the row space. Guys with me? Okay. We also had to find a basis for the null space of A. And we did that. How? Well, basically, when you did your work here, you basically solved take matrix A and set it equal to 0, 0. You basically have these statements here for the null space. So this was that work that I did here. Basically, what's on MATLAB is this, right? when I said find a basis for the null space, when we got it into this form, you could see x has to be the same as z. So x is equal to t, y is equal to negative 2t, z is equal to t. So a good answer would be the single vector 1, negative 2, 1. That's a basis for the null space. So here's a basis for the row space, or this one. Here's a basis for the null space. Okay? Last thing, find a basis for the column space of A. Now, how do you do that? Well, again, we're looking at the columns, right? So what the book says is a good idea, and I kind of like this. Do reduced row echelon form of A, but there's a problem. The problem is that the row ops change the column space. So that's a problem. But what you can do now is you can use the pivots to decide which columns of the original matrix you can use, or you should use. So when I did reduce row echelon form of A, it looked like this. It was 1, 0, negative 1, 0, 1, 2. Do you remember what I meant by the pivots?
Isn't that like 1 and 1?
Yeah, so the pivots are the leading, the non-zero coefficients, right there. And since those are in columns 1 and column 2, that tells you that these would be a nice basis for the column space. So basis for the column space, my answer would be, maybe I take column 1, 1 and 0, 1. There's a basis for the column space. 1, 1 and 0, 1. Okay? But what's a nice fact, okay, another nice theorem, is that the dimension of the row space of A will always equal the dimension of the column space of A. And you might say, why is that? That's in the book, but that's a nice little fact. In our case, 2 equals 2. That's what's called the rank of a matrix. Basically, what this is saying, another nice fact, which is related to this, is that the rank of A is equal to the rank of AT. And that's kind of surprising, I guess. Yeah, Anthony.
So for your favorite matrix, when you do reduced row echelon form,
Yes.
the basis for that would be
Basis for what?
for your favorite matrix, for column, sorry.
Okay, for column space. Yeah, let's go back to that example. I think this is good to get nailed down. So I had my favorite matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9.
And then
I did reduce row echelon form of this, and I got 1, 2, oh no, we actually did it all the way. So we got 1, 0, negative 1,
yeah,
and then we got 0, 1, 2,
and then the last row is just all.
and 0, 0, 0. Yeah.
So it would be the first 2 rows you would use for your basis then, because that has the leading coefficients of 1.
So you see these leading coefficients of 1, So we could say a basis for the column space, is that what you're asking?
Yeah, column space.
Would be given by 1, 4, 7
Gotcha.
and 2, 5, 8. That would be a basis for the column
So you have
space.
to go back to your original.
Yeah, because what happens is when you do row operations, it changes the column space.
Okay,
Yeah.
sweet. Okay, good.
Cool. So